Recording in progress.
Okay, so let's say just put this in context. In general, a linear transformation T v1 v2 is going to equal an arbitrary linear combination of v1 v2 for each of two components. We can easily calculate that image either by a matrix or just by doing the arithmetic of the transformation. We can also calculate the preimage of a given vector. We call it W. So we want the preimage of this vector, which is the vector over here that gives us this vector over here. And we see that we can reduce the process of doing the preimage to, well, this equation, which means the first component equals the first, second component equals the second. We get two simultaneous equations. We can solve for v1, v2. Maybe we get a solution, maybe we don't. Maybe we get a degenerate solution, a solution that gives us one free variable. Then down here we can see that we could also take this system and express it as a matrix equation, as we could for this calculation. Let's do a specific example and then look a little bit at the geometry of the situation. Okay, T of 3, negative 4, where T of v1, v2 is this transformation where I specified the constants that I indicated previously as A, B, C, and D. Now it's 2, negative 1, 1, 1. Okay, the image of V equals 3, negative 4. Well, T of 3, negative 4 equals 2 times 3 minus negative 4. And I don't need parentheses, but since I've written it, I'll go ahead and use it. 3 plus negative 4. And that equals, arithmetic is easy, so I'll probably mess it up, but that's going to be 10. And this is going to be negative 1. Now we can visualize this image here of the vector V. We can do that as follows. V is the vector 3, negative 4. So I'm going to write that kind of small, but so if we have 3 here, negative 4 here, here's our V. And then we can visualize this as a transformation that takes this vector, and let's go ahead and use a reasonably consistent scale, takes this vector to the vector 10, negative 1. So if 3 is here, then 10 is going to be 1, 2, 3 times that far, and then a little bit more. So here's 10. Let's say here's negative 1. So we can project over here. And here's our image. This vector is what we're going to call W. Negative 1. We see that this transformation then has taken this vector and rotated it to this angle and stretched it out. In your homework, in WebAssign, the pictures will often show these two vectors on the same set of coordinate axes. I prefer to think of your vector and your image, or if you wish, your image and your preimage. However, just to make sure you see this the way you probably see it on your WebAssign homework, if we're using WebAssign in this particular course, this would look something like this. I'm going to use a slightly different scale. So here would be our vector v, here would be our vector w, and you see what happens to v. I think you can see it just as well here. But no problem either way. It's pretty easy to see what's going on. Okay, now what about the preimage of w? Well, let's just ask ourselves, looking at the geometry of the situation, what if we had a vector w out in this direction and we wanted to find the vector over here? Okay, now it's kind of unpredictable. You might think by looking at the way this transforms here that to get a vector over here you'd have to transform a vector that rotates it in some way similar to this. You can't really predict that until you develop some machinery when you can see what happens. In any case, the preimage of this vector w, and let's say w equals a vector up in this direction. Let's say it's 5, 7. Okay, preimage of the vector w equals 5, 7. This means we have to solve v1, 5, 7. Can aim things very well here for v1 and v2. So we write out this equation. So 2v1 v2 is 2v1 minus v2, v1 plus v2, and that has to equal 5, 7. In other words, this is the equation. I should have left myself a little more room, but the equation T v1 v2 equals the w vector. So how do we solve this equation? Well, this implies that 2v1 minus v2 equals 5, and v1 plus v2 equals 7, which implies the augmented matrix 2, negative 1, 5, 1, 1, 7. We can reduce this augmented matrix and we find v1 and v2. Alternatively, we could write this as a matrix equation. Here's your matrix, and then that's times a column vector v1, v2, and that should equal 5, 7, so you can invert that matrix and calculate. To get the geometry, we might as well go ahead and reduce this matrix. So I'm going to skip a step here, but this matrix, I'm going to switch the first and second column. And there we have it, and I did that just so it'd be easy to get a 1 here. Then we're going to subtract 2 times the first row from the second. And that's easily done, even though I might screw it up, so watch me. Okay, well, obviously if I subtract twice the first row from the second, I'm going to get 0, because that's why I subtracted 2 times the first row from the second. And then subtract 2 times 1 from negative 1 is going to give me negative 3. And subtract 2 times 7 from 5, that's going to be negative 14, and 5, that's going to give me negative 9. And coincidentally, or conveniently, I didn't set it up that way, I am going to get an integer down here. This gives me 1, 1, 7, 0, 1, 3. And at this point, I could take this another step. I could subtract this row. Well, I might as well subtract this row from this row. And that gives me 1, 0, 4, 0, 1, 3. So V1, V2 equals 4, 3. Now it was extremely unlikely that when I just wrote down these numbers here, I actually would write down numbers, and this board is, okay, let's clarify it. Okay, this board is a little further over there, I should have checked that. V1, V2 is 4, 3. Now what does that tell us on this picture? That tells us that if we take the vector 5, 7, okay, and I've got to exaggerate a little bit, but let's say 5, 7 is here. That when we map this by the transformation, we get our target. Now W was 5, 7, V's 4, 3. Okay. Now I'm going to have to mess up my picture, which I kind of hate to do. And let's see if I can make this as neat as possible, because I find that the zoom version here tends to really do badly if I have smudges on the board. And I don't know if that's a characteristic of Zoom or my ISP. So this was 3. And now we have the vector 4, 3, which just happens to be perpendicular to the vector 3, negative 4, worth noting. Okay, so that'll be about here, and it looks pretty much perpendicular. That's just pure coincidence. There's no reason it should have come out that neatly. This vector transforms over to our target vector, which was 5, 7. So if there's 10, here's 5, here's 7. So if our V vector is this, our W vector is the vector 5, 7 that we specified. Now note a couple of things. These vectors just happen to make a right angle, which is sort of convenient. Okay, this is a right angle. This angle is less than 90 degrees. So from the obvious connection, or the obvious comparison of these angles, we see that this transformation doesn't preserve angles. Okay, so just a note, a side note, because this is an important thing, do we have an angle preserving transformation? Transformation doesn't preserve angles. That's an idea you just kind of want to get in your head now, It's not going to be in your homework this time, angle preserving, although we could easily do it. You'd easily use the dot product to verify that this angle is 90 degrees and calculate this angle. The dot product of these two vectors is 50 minus 7. That's somewhat bigger than I would have expected, but it's 43. If you divide by the product of these magnitudes, yeah, you find that the angle, the cosine of the angle is pretty small. It's fairly close to 90 degrees, but it's not 90 degrees, okay? So it's not an angle preserving map. Okay, so bottom line, what you want to see is how to calculate the image if you're given your v vector, the components of your v vector, and how to calculate the preimage if you're given the w vector over here. So we were given this vector, we calculated this. We were given this vector, we calculated this.